consequence. So we're leaving out that right now. We'll come back to that probably on Thursday. But for now, what a stock does for you is you don't really run out of it. You just having a big stock makes it cheaper to get OL. That's all. Yeah. Yeah, I was worried about that too. Let's see. I'm also worried about this being in the wrong place. Let's see. Yeah, it looks like I have a sign wrong for that part, doesn't it? We can compare that to the top expression there, which is the supply function for this general case. So I just must have a sign wrong. So that must be. I'm going to assert that must be -1. And I'm sorry. So Hillary, what's your name? Mark. Hillary and Mark deserve an extra credit point for that, Jeff, please. Okay, so I should fix that here also. It's correctly written here. Okay, so now I want to do something which I think is kind of neat. We can go back to these data we had on. I want to go back to these data and focus on the inverse supply function here, and use these data to see what we can say about global oil supply. So what we see here, we see how much a firm is producing at a point in time based on their stocks. We've talked about there being variation in the underlying costs they have of exploiting the stocks they have, but we don't have direct data right now on those differences in costs. So we've said, well, gee, it's expensive to get oil out of tar sands, it's cheap to do it in Saudi Arabia, but those are just words, not numbers. So let's see if we can back out some numbers from these data. And we can. Something we can do, which is really cool here, I think, is to use these data along with this description of the solution to the firm's problem to actually estimate what the BIs are up to a common factor, up to a common proportion. Okay, so let me just do an example of this. The example I'm going to have is a North American example. So I'm going to consider just production in the U.S. and production in Canada. So the U.S. is certainly not the lowest cost oil producer in the world, but their costs are considerably lower than Canada's. And so what I want to do is this. I want to compute the ratio of Canada's technological parameter BI to the U.S.'s parameter BI. So in particular, I'm going to be estimating and figuring out, we'll call it DUS divided by DCAN for Canada. So and these are going to be, we're hoping that these will capture the differences in costs of exploiting the stocks available in the two different countries. Is the exercise clear? Okay, so the claim is we can use that data out there to do it. So let's see how this goes. Well, so one way to get this, I want to actually need to do a trick with this thing here first. I'm going to observe that I can rearrange this thing so that I get an expression y sub I over si, and that's going to be equal to this stuff, alpha plus beta times p, alpha plus beta, 1 minus alpha minus beta, times this stuff, w alpha r to the beta, bi. D down here, 1 over 1 minus alpha minus beta. So, pulling this out, or I should say explaining this, notice the only place that the BI shows up, the only thing that's idiosyncratic is this BI here. The other stuff doesn't vary. So as a consequence, the ratio of BUS to BCAN involves all this stuff canceling out except the betas. So we'll wind up here with an expression that involves YUS divided by SUS, so the stocks in the US, divided by YCAN, divided by SCAN. This whole thing raised to the 1 minus alpha minus beta. Is it clear how I got that? Is it? Yes, sorry. Oh, I'm certainly. I think the answer is no. Actually, look at the. Oh, you say in the inverse supply function. I think I erased the general form here, didn't I? I'm going to. Yeah, I think it's okay. I mean, in this equation here, si and yi both appear without exponents. They appear, similarly here. They have the same exponent. I think it's okay. Okay. So sorry. And so this ratio is equal to this ratio. Does everyone see how I got from that box statement to this one? Yes. Yes, that's right. So everything that doesn't have an I is the same. So we're assuming that the prices P are the same, and that's quite there's a global market for oil for sure. So I'm not too worried about that one. Yeah. So last lecture we talked about their labor not being mobile across countries. So maybe we relied on there being big differences in manufacturing wages, for example, last time. So you might worry about that. Maybe I'm basically going to punt on that, assuming they're the same. I could maybe defend that by saying that multinational oil firms tend to bring in workers, so maybe oil worker labor is mobile. But I'm not going to waste too much time on that. Yes. The way I got here was to solve this thing for B. Let's just see if let me undo that. So this implies that DI is equal to YI over SI, all raised to the 1 minus alpha minus beta times some other constant M that depends on this stuff, the prices of B and so on. Is that clear? So I solve for B from this thing, and I wind up with this ratio raised to this power, and then some stuff that depends on prices and alphas. Is that clear enough? Okay. I see nodding heads. I see nodding heads. Do I see any shaking hands? Are there? No shaking hands. All right. So from here to here, that gets us to here. So to get this ratio of B's for the U.S. and Canada, we can just plug in these numbers, these ratios from here. So for the U.S., we see that the ratio is 28.95. And for Canada, we see that it's 1.5. thing's all raised to the 1 minus alpha minus beta. And so if we divide 28.95 by 1.5, I believe we get a number on the order of 19.3 raised to the 1 minus alpha minus beta. So that's telling us something about the b's. We don't know, what the alphas and betas are necessarily. I waved my hands last time and said, well, assume alpha is equal to 0.6, and that was a case where we had constant returns to scale, though. Here, let's go ahead and assume what we did earlier. If we let alpha plus beta be equal to 1/2, then that implies that b us divided by b can is equal to 19.3, square root of 19.3, which is about 4.4. So what's the interpretation of that number? The interpretation is that the productivity of a typical U.S. oil well is 4.4 times greater than it is in Canada, or alternatively, the costs of extraction for the U.S. firm are 4.4 times greater. Or sorry, costs are 1 over 4.4 times. Okay, so we can use this kind of data on production as a percentage of reserves to back out a lot of information about these different technological parameters. Okay, is that clear? Is the exercise? All right. Now, somebody made this point earlier. I think it was perhaps it was Scott. There's a couple things missing from this. I mean, actually, I like this as a description of the problem facing a firm at a point in time for extracting stuff. But there are a couple important missing pieces to the story here for a sort of more complete model. One thing that's sort of funny here is that, at least in principle, there's nothing in the production function to prevent firms from extracting more than they have in their reserves. The S parameter, treating as reserves, affects the price that a firm faces for extracting stuff. But as long as that's a positive number, they can extract more. So that's a little unrealistic. And there's another sort of obviously false assumption, or sort of a problem with the model, if you like, is that there's no trade-off here between extracting oil today and extracting oil tomorrow. It's just a static model. The S's are affecting the cost of extracting oil today, and then the world is. That's the way the model works. So if we're interested in the dynamics of oil extraction, and for a lot of reasons we should be, we want to be able to think about firms making a choice to extract today, and that could depend on the level of the stocks and the way we've already modeled. But then you'd like it to be the case that if they extract a lot today, their stocks tomorrow are smaller, so that their marginal costs tomorrow of extraction are greater than they would have been otherwise. Okay, so those are a couple shortcomings in this model. I'm going to briefly, we don't have much time, so let me briefly talk about a couple alternative ways to tackle this. So the first thing I want to do is just deal with the issue that you might be able to extract more than your stock is. And so this is a simple solution. It's closely related to the problem on problem set 7. So something we can do is just change this a little bit. So what we can imagine making it so that we have a production function just as we did before. So this thing inside here is the production we had before. And just as a sort of a hack, what we can do is make sure that y is either equal to that or else it's equal to the total amount of stocks firms have, and not more than that. So this is just a quick fix for the problem of stocking out your reserves. I'm going to quickly draw sort of compare what the supply curves might look like in that case. Okay, so here's y, here's p. We've got these expressions for, actually we're interested here in the inverse supply function. So you can see that p is equal to this ratio of y over si with these other b's kicking around. If we have the case where alpha plus beta is equal to 1/2, we talked about that case as well. In that case, these supply functions are linear. So for a case where alpha plus beta is equal to 1/2, we might have this. But we also have something like this. If this is the supply curve for country 1 and this is the supply curve for country 2, which country has the larger stocks? Oh, it's a trick question, actually, because we also have these DIs running around. So look at the inverse supply. The SI shows up here, but then the DI also shows up here. So which is the more productive? Let's do it that way. Well, at a given price, this country produces a lot more oil. It does so because it faces lower marginal costs. So this is the more productive firm. So these are the supply curves you have for the firms here without this restriction that you can't use up your total reserves. If we impose this thing, what we might do is say that this country, for example, might have, let's call this country 1 and call this country 2. This might be country 1's reserves. And this might be, say, country 2's reserves. So S1 and S2 might look something like that. If we impose this restriction, then the way the supply curves will look is they'll, for country 2, they will go up until you hit the stockout point, and then what will they do? What's that? Yeah, y can't increase further than that, so it'll go straight up. Similarly here, so country 1, oops, I didn't mean to draw that there, I need to draw it here. Country 1 will go out until it stocks out, and then again, its supply curve goes vertical. Okay, so with those two, by the way, what does aggregate supply look like if we have this stockout restriction? Price of 0, what's aggregate supply? 0. It'll increase, it'll increase until we hit the lowest stockout point. Actually, that's another question. Who's first to stock out? Firm 1 is the first to stock out. Who has lower reserves? Firm 2. So, but despite the fact they have less oil, country 2 here stocks out last. Why is that? What's the rationale? Yeah, that's right. So firm 1, you can see they've got a bigger SI here. They stock out at this point. The reason they stock out first is because they have a better VI. They have a larger VI than firm 2 does. So even getting out their last barrel of oil is lower cost than firm 2 getting out less than its last barrel of oil. So they're a more efficient producer, and that's reflected here. Okay, the aggregate curve, though, is going to be, it'll go from 0 to a horizontal summation, so something like this. So aggregate, and then where does it go from there? Well, actually, at this point, firm 2 hasn't stocked out yet, so this will have a slope equal to firm 2's production for a little bit, until we get to the point where firm 2 stocks out, and then we'll go fully vertical. Okay, so it's piecewise, so 3 pieces. along the segment, both firm 1 and firm 2 are producing. Along the segment, just firm 2 is producing additional oil, and above this, both of them are stocked out. All right. Okay, let me leave you with a question. The question is, if you have a supply curve that looks like this aggregate supply curve, you might think about what the elasticity of supply is as you move along that curve. And with that, let me stop, and I'll see you Thursday.